This thesis explores a new framework for gravitational structure formation, driven by scalar field dynamics within an affine-extended spacetime. The theory, termed Gravito-Scalar Inflation, proposes that a pion-mode scalar field acts as a symmetry-preserving source of localized inflation and geometric modulation. Coupling through torsion and curvature, this scalar field gives rise to gravitational effects traditionally attributed to mass and cosmological constants, without requiring dark matter or symmetry-breaking mechanisms. This work situates the scalar field within a non-Riemannian geometric background, extending the affine connection to account for torsion and non-metricity as dynamic contributors to space-time evolution. The approach embeds general relativity within a broader Einstein-Cartan-inspired framework, treating geometry as an adaptive, field-responsive medium. Gravitational physics has long been shaped by the twin frameworks of general relativity and quantum field theory. However, several cosmological anomalies, such as the Hubble tension, non-Kerr black hole imaging, and flat galaxy rotation curves, suggest that our understanding of gravitational structure is incomplete. Classical inflationary models, while powerful, rely on symmetry-breaking scalar fields inspired by the Higgs mechanism and require a universal cosmological constant. These models generate mass through spontaneous symmetry breaking and drive inflation through dominance of vacuum energy. This thesis introduces an alternative approach based on a symmetry-preserving scalar field that operates within an extended geometric background. Rather than invoking mass generation through broken symmetry, this model proposes that a pseudo-Goldstone boson, specifically a pion-mode scalar field, actively modulates gravitational structure through coherent configuration. This leads to localized inflationary behavior and structural modifications in spacetime with no need for exotic matter or universal inflation fields. The scalar field is embedded in a modified affine connection that extends the Levi-Civita structure of general relativity. This extension is inspired by Einstein-Cartan theory and metric affine geometry, where torsion and non-metricity are promoted to active degrees of freedom. In this setting, the scalar field not only evolves within spacetime, but also contributes to shaping its connection, thereby participating in the dynamic generation of curvature and causal structure. This affine-based generalization provides the foundation for reinterpreting mass, gravity, and expansion as products of internal geometric responsiveness rather than external substance. The central element of this model is a real massless scalar field, identified with the pion-mode and interpreted as a pseudo-Goldstone boson arising from chiral symmetry breaking. Unlike the Higgs field, which destabilizes symmetry to produce mass, the pion-mode scalar preserves symmetry through its coupling to the axial vector current. This axial coupling acts as a source of internal coherence and directional interaction, allowing the field to generate gravitational effects without altering the underlying symmetries of the theory. So, the scalar field evolves in accordance with a Klein-Gordon type equation, but, it's set within a dynamically evolving geometric background. This equation actually accounts not only for the usual curvature, but also for torsion and non-metricity. The scalar field's gradients and coherence, they influence the structure of spacetime, introducing localized tension and curvature effects that, in turn, propagate through gravitational interactions. The Gravito-Scalar Inflation model is basically situated within a non-Riemannian manifold that permits both torsion and non-metricity as physical degrees of freedom. Unlike traditional general relativity, which restricts the affine connection to a metric-compatible and torsion-free form, this framework adopts a more general connection structure that dynamically responds to scalar field gradients. Within this setting, the scalar field does not simply evolve on a passive geometric background, but instead participates actively in shaping it. As the pion-mode scalar field varies both spatially and temporally, it generates a geometric tension tensor. This tensor contributes directly to the gravitational field equations by modifying local curvature. Now, crucially, the nature of this modification depends on how the scalar field interacts with different components of the extended geometry. Two distinct gravitational modes actually emerge from this interaction. The first is the gravito-strong mode. which arises through the scalar field's coupling to spacetime torsion. This interaction is typically short-range and becomes significant in environments with steep field gradients, such as compact astrophysical objects or high-energy density zones. The second is the gravito-weak mode, which is modulated through the scalar field's coupling to spacetime curvature. This coupling produces broader, long-range gravitational effects, particularly influential at galactic or cosmological scales. These modes are not governed by the scalar field's mass magnitude, as is the case in Higgs-type mechanisms. Instead, they are modulated by the modality of the scalar boson, that is, the scalar's coherent configuration and its symmetry-preserving coupling to the axial vector current. This means that gravitational structuring in the model is not a result of spontaneous symmetry breaking, but of dynamic geometric feedback informed by the scalar field's evolving structure. In this way, Gravito-Scalar Inflation extends gravitational dynamics beyond traditional tensor-based interactions. It frames torsion and curvature not merely as passive outcomes of energy distribution, but as responsive features shaped by internal field architecture. This enables the model to describe inflation, structure formation, and gravitational anomalies without recourse to external energy inputs or exotic forms of matter. In this framework, inflation does not arise from a universal scalar field driving exponential expansion. Instead, it emerges locally in zones where the scalar field's potential exhibits flatness or slow roll behavior. These regions experience a temporary coherent geometric expansion, similar in outcome to classical inflation, but distinct in origin. The inflation is structurally induced, not energy-dominated. These localized inflationary pockets occur in high-energy or highly structured environments, such as around black holes, quasars, or during compact object mergers. The scalar field maintains coherence across these regions, allowing inflationary behavior to occur without the need for symmetry breaking or an explicit inflaton field. The result is a modular, adaptive form of inflation that integrates seamlessly with observational data. The Gravito-Scalar Inflation model generates several testable predictions that align with observed astrophysical phenomena. It suggests that brightness asymmetries and distortions in black hole photon rings, such as those observed by the Event Horizon Telescope in M87 star and Sagittarius A star, arise not solely from relativistic spin, but from scalar-induced perturbations of light paths. These deviations reflect modifications to null geodesics, caused by the localized geometric tension induced by the scalar field. The theory also accounts for observed delays between gravitational wave and electromagnetic signals in neutron star mergers, including GW 170817. These delays are interpreted as propagation through localized inflationary zones formed by coherent scalar pockets. Such regions act as refractive media, altering signal arrival times in a way consistent with observations. Flat rotation curves in galaxies like NGC 3198, traditionally attributed to dark matter, are instead explained through scalar modulation of halo geometry. In this view, the gravito-strong interaction creates affine curved structures in the outer regions of galaxies, eliminating the need for non-baryonic matter. Timing irregularities observed in pulsars, including anomalous noise and precession in systems like PSRB 1829-10, are explained by unresolved scalar tension in regions with strong torsional interactions. In contrast, more stable systems such as PSRB 1257+12 are seen as indicative of scalar relaxation. Finally, the model predicts the emergence of redshift drift anisotropy over long observation periods. This anisotropy reflects directional differences in scalar field structure, implying that inflationary effects are not isotropic, but instead driven by the spatial configuration of coherent scalar plateaus. These predictions are testable with instruments such as the Extremely Large Telescope, the James Webb Space Telescope, and large-scale timing arrays. Gravito-Scalar Inflation, presents a symmetry-preserving, field-structured alternative to the usual inflationary cosmology and dark matter frameworks. Instead of relying on mass generation, it introduces structural modulation and, Well, it replaces global inflation with this idea of localized, geometry-driven expansion. By extending the affine connection to include torsion and non-metricity, and embedding a coherent scalar field within it, this model actually provides a unified pathway for explaining gravitational anomalies, field curvature feedback, and observable astrophysical behavior. It really invites continued exploration, observational verification, and of course, ongoing theoretical refinement. If Gravito-Scalar Inflation turns out to be valid across all meaningful scales, it would actually represent a pretty fundamental shift in our understanding of gravity, coherence, and causality in the universe. Philosophically, it would redefine gravitational causality as a structurally emergent phenomenon, rather than just a passive consequence of mass energy content. In this view, causal relations in spacetime wouldn't be fixed by inertial mass alone, but would instead arise from the coherent structure of scalar fields interacting with geometry. This, in turn, would allow for local, context-sensitive variations in the flow of time and space, driven by field configurations rather than static constants. Coherence would become the organizing principle of cosmology. Instead of, entropy gradients or initial condition fine-tuning guiding cosmic evolution, the alignment and structure of scalar fields would serve as the fundamental determinant of order. Coherence would not be a temporary or derivative property, but a sustained, geometrically active influence. Inflation, expansion, and large-scale structure would be recognized as emergent consequences of scalar field integrity rather than the result of symmetry breaking or mass dominance. The necessity of mass as a fundamental gravitational source would also be called into question. In this framework, mass is not the cause of curvature, but one of its possible expressions. Scalar field modality, rather than rest mass, would become the primary agent through which spacetime responds to matter-like effects. This would allow for the reinterpretation of mass itself as a geometric artifact of field structuration, dissolving the boundary between substance and structure. Psychologically, these shifts invite a reinterpretation of internal experience. Causality, often perceived as externally imposed through events and trauma, is here understood as emerging from internal coherence. The self becomes an agent not through reaction, but through field alignment. Growth and transformation result not from accumulation or force, but from structural resolution. The metaphor of inflation shifts from one of expansion driven by energetic dominance to one of coherent unfolding. Identity becomes fluid and emergent. Just as mass is seen as a byproduct of structure, identity is reframed as a reflection of the scalar coherence within a person. Stability, influence, and presence arise from alignment, not volume or intensity. Psychological presence, like gravitational presence, becomes a function of internal configuration. Agency becomes less about overcoming forces and more about generating gravitational pull through coherence. Taken together, these implications suggest that both the universe and the self are shaped by the quality of their internal structuration. Gravito-Scalar Inflation thus offers not only a new cosmology, but a new metaphor for understanding the architecture of awareness and the structure of becoming.